Hi everyone, welcome back to another heat and mass video. We're starting homework 4 today, and so I just have my paper here once again, and I've just written on the front what our agenda for this video is today. So we're going to be talking about a lot of different things relating to diffusion. So we're going to start by talking about some diffusion coefficients in both the vapor and the liquid phase. And that's going to also look at how the Vignier's formula and the Stokes-Einstein equation relate to each other. And then after that, we're going to be talking about the equation of continuity for a specific example. Third, we're going to talk about the equimolar counter diffusion at a a vapor liquid interface, and how that is going to look like. And then lastly, how the total flux is going to relate to specific flux of a component if they have some sort of balance. So if A is going to output 2B, how the molar flux of A will relate to the total flux. And then same for if it's 3A emitting 1B, how that's going to change at a catalyst surface. So on my page right now, I just have that written, all of the things that we'll be looking at today. So I'm just going to move this over a little bit so I can hold it up like this for you. And then, yeah, you can see that. Okay. So I'm just going to begin by writing these coefficients for vapor and liquid if we're talking about diffusion. So for vapor, so if we recall, these diffusion coefficients are going to be in units of meters squared per second, and that's something that we found in a couple of other videos before. So for vapor, we have 10 to the negative fifth, and then for liquid, 10 to the negative eighth. Sorry, 10 to the negative ninth for liquid. So one specific equation that we're going to look at is the Leonard-Jones potential. So this is one equation that can help us solve for the diffusion coefficient. So once again, our diffusion coefficient is represented by capital D, and then we're going to have the subscript AB to show how component A is diffusing within component B. So DAB is going to be equal to 0.00266. So this was found experimentally. This is a value that's not going to change depending on what your components are. And then that is going to be multiplied by our temperature, so whatever temperature our system is at, to the 3/2 power, all over, divided by our pressure, so the pressure of our system, that's also going to be known. And then we're going to multiply that by our average molecular weight of both A and B together. So I'm going to represent that by a capital MAB, so that's just taking what the average molecular weight is of A and B together for our whole system. And then that will be multiplied, I know this is a lot, and then that will be multiplied by sigma squared, which represents the diameter between the collisions. So the collision between our component A and component B, whatever that distance is between those particles is our collision diameter here. And that's what that's represented by. And lastly, that will be multiplied by omega, which is going to represent the collision integral. So when you have this whole equation written out here, this is what you'll have. So once again, the 0.00266 was found experimentally. That's going to be the same. Then we have our temperature, our pressure, our average molecular weight, our collision diameter, and then our collision integral. And I also forgot to say that the average molecular weight will be to the 1/2 power here too. And so this omega here, which is our diffusion collision integral, this value is based off of the temperature of our boiling point. So TBP, temperature of our boiling point. And so that seems like, sorry, there's something in my eye. That seems like a big long name, diffusion collision integral, related to the temperature of our boiling point. And so to kind of break this down a little bit, we can see that our temperature for the boiling point is related to our T star, which we know an equation for. So T star is going to be equal to our Boltzmann constant. So once again, that is known. And so that's like easy to plug in. And then the temperature of our system. So Boltzmann constant times the temperature of our system here. And then that's going to be divided by the activity force between the collisions of A and B. So that'll be represented by that like sigma, the curly looking E. Here, I have it written here. So just to break down the diffusion collision integral, it's relating to the temperature of our boiling point, which is the T star equals our Boltzmann constant times temperature of our system, and then like the energy between the molecular force interaction of A and B. And so since this is related to our boiling point temperature, this will be for estimating vapor diffusion coefficients. So this is for vapor specifically. So like I said at the beginning of the video, we're going to talk about a couple of equations to estimate diffusion coefficients for vapor and liquid systems. And this Lennard-Jones potential equation is specifically for vapor. So we have that written here. One important thing to say about this equation is to make sure that your units are remaining the same. So typically when you solve for this equation, your diffusion coefficient will be in centimeters squared per second rather than meters squared per second, which is not a big deal, but that's just something to keep in mind when you're plugging all of these values in. And then also for our pressure, that is typically represented in bars rather than atmospheres or pascals. So that's just another thing to keep in mind. Okay, so now that we've looked at our vapor equation, we're also going to write one for liquid now. So I'm just going to put liquid on the side here. And so the equation we're going to look at for this one, similarly to how we looked at the Lennard-Jones potential for vapor, we're now looking at the Stokes-Einstein equation. And so now that we're looking at a liquid system, this is going to be a little bit different from the vapor. So when we were looking at the diffusion coefficient of A and B, both A and B were vapor particles, so it's just kind of seeing how those interact in the air, how far apart they are, how the diffusion collision integral, so how those collisions happen, things like that. Now that we're looking at liquid, we're going to be looking at a dilute mixture. So all that this means is that there's going to be some sort of solute within a solvent. So if you recall, solvent is like the liquid base that you have, and then the solute is whatever is being dissolved in that liquid. So for this, when we write DAB, we're referring to A as being the solute and B as being the solvent. So that's just saying how A is going to be diffusing within B. So A is like that particle, and then B is going to be that liquid. And then for the Stokes-Einstein equation specifically, this is looking at our infinite dilution diffusion coefficient. So that just means over an infinite amount of time, what is this diffusion coefficient going to look like? So we represent that by a little open circle, so like a little 0, a little degree sign, looks something like that. So that'll just be represented here like this. And then this equation is going to equal our Boltzmann constant, which I had mentioned just prior in that Leonard-James potential equation. So our Boltzmann coefficient times the temperature of our system, all divided by 6 pi. So that's just a constant that they found from this equation, times the radius of A times the viscosity of B. So when we're talking about radius of A, once again, A is going to be our solute. So it's just saying what the size of these particles are, what that radius is for each of those particles that are being dissolved in the liquid base. And then viscosity of B is just saying the viscosity of our solvent base. And so this is what I have here. We have the infinite dilution diffusion coefficient of A and B is equal to the Boltzmann constant times the temperature of our system, divided by 6 pi times the solute radius, so the particle size, times the viscosity of the solvent. And then, like I said at the beginning of the video, we're going to see how the Vignier's formula and the Stokes-Einstein equation are related to each other. So the whole basis of the Vignier's formula is based off of the infinite dilution coefficient, which is found through the Stokes-Einstein equation. So that's that DAB with the open circle above it represents the infinite coefficient, diffusion coefficient. So then for the Vignier's formula, so the Vignier's formula is going to estimate our diffusion coefficient of A and B, so that DAB, but not the infinite one like the Stokes-Einstein equation was, but it's going to equal the infinite diffusion coefficient raised to the power, the infinite dilution coefficient of A and B raised to the power of the composition of B. So that's just saying what percentage of this entire system is composed of B, of molecule B, whatever it is. And that's going, that infinite diffusion coefficient that we find from the Stokes-Einstein equation will be raised to that power times another infinite diffusion coefficient, but instead for B to A will be raised to the composition of A. So if all those words didn't make any sense, this is what it looks like. So we use the Stokes-Einstein equation here to plug into our Vignier's formula, because we have to use that infinite diffusion coefficient here. But when you're looking at A being diffused within B, you need to raise that to the power of the composition of B, and then vice versa for when B is being dissolved in, sorry, that B is not very clear. And then for when that B is being dissolved in A, you have to raise that to the composition of A for the entire system. And so that is our Vignier's formula, and kind of shows like how it relates to the Stokes-Einstein equation. And then you can use this, you can use this Vignier's formula so the actual infinite dilution coefficient of A and B and B and A is something that you can typically look at knowing what A and B are. So if like you know what component A is and what component B is, you can do a Google search and find what those infinite coefficients are, because they're usually known values. And then you can see how the percentage that you have of B and the percentage that you have of A in your system is going to affect your diffusion coefficient and relate that back to your Stokes-Einstein equation. So those are pretty well related to each other, very important equations for liquid systems where you have that dilute mixture. So now we're going to talk about the equation of continuity when you're looking at a one-direction system. So I'm going to go ahead and move over to this page. So we're going to start by drawing out our system. So we're just going to have a cube here with some sort of dedicated volume. So we'll just draw our little 3D cube here. And so this is not unlike anything that we've seen before, but we're going to be seeing how this equation of continuity works when we're looking at a one-direction system. So this, like I said, this is very similar to what we've looked at before, with some sort of flux going in some direction. But the way that we've looked at it before is we've had some sort of flux coming in, some sort of flux coming out, and we haven't really accounted for any sort of accumulation within the system that we're looking at. We would usually just evaluate something coming in, something going out, how that changes with like the growing rates and stuff. And so now we're going to see how that changes and what it looks like if we have some sort of rate of formation. So I have my cube here. I'm going to go ahead and label all the axes. So we're going to look at Z, DZ as like that bottom one, because the direction that we're going to show that we're going in, that unilateral or unidirectional direction, the one direction is going to be Z. And then for our other axes, we're going to have y, dy, and then x, dx. So I just have my little cube here. I've labeled z, dz as the bottom direction, and then the vertical is x, dx, and then that one going into the page is y, dy. So we're going to show some sort of flux coming in the z direction. So flux represented by a capital letter N of component A. We're just going to be looking at how component A is going to be flowing in the system at position Z, and then how it's coming back out, so NA at position DZ instead. So that's just what I've drawn for my arrows. We have the flux of A coming in at position Z, flux of A going out at position DZ now. And so, like I said, we're going to have some sort of rate of formation. So we're going to dedicate RA, capital RA, as being that rate of formation of A. And like I said before, our typical energy balance is going to be some sort of in minus out plus our accumulation, which in this case is our formation. That just means the same thing here. So we have the rate of formation equaling RA, so that's how A is going to start forming in this cube. And then we have our influx minus our outflux plus whatever formation rate that we have here. So now we can plug in these values that we know. And so for our in, we're going to have the NA, so the flux of A at position Z. And then we can't forget that all of these will be relating to some sort of volume, because we're looking at the cube as a whole. Even though we're only trying to look at one direction of flow, we're still looking at the entire volume of the cube. So since we already have accounted for the Z direction, we have to multiply that by the area of the square that it's going through. since we're already going in the z direction, we just have y and x left. So we'll have to multiply that flux of A at z by dx dy to consider the volume here for all of these sections. And then that'll be subtracted by the flux of A at position dz, so that's our final position, still multiplied by dx dy. And then we have to add our accumulation or our formation rate. So we have Ra, which is just encompassing our entire rate of formation of A within the cube. And that also has to be multiplied by our volume because, once again, we're looking at the entire volume here. So dx, dy, dz. And then this entire thing is going to be equal to the concentration of A times that volume, once again, dx, dy, dz, all over change in time. So that's kind of seeing how our concentration is going to be changing through this entire volume divided by the change in temp or in time. And that'll kind of encompass any sort of changes that we have from what's coming in minus what's going out plus the formation rate that we have. So I will show you here what I have on my page. So this is everything that I just said, just to double check that you have this down. And so our goal from this equation that we've developed is to get this in the form of the traditional equation of continuity, which is a well-known equation. You could just simply look that up, find that anywhere. So I'm going to write this up here just so we have reference. So it'll be the gradient of the flux of A plus our change in concentration of A divided by change in time minus the rate of formation is equal to 0. So this is our equation of continuity up here. So we have gradient of A plus change in concentration of A over change in time minus the rate of formation of A equals 0. And so we're trying to simplify this big old equation into that one up there. So the first thing we're going to do is divide by our volume from both sides. So now we're going to have, the flux of A at position Z divided by dz. Since we only multiplied by dx dy, we have to divide by dz. And then same thing for our flux at dz. That'll be divided by dz as well, plus our rate of formation equals change in concentration of A over change in time. So this is our simplified equation we have after we have divided by our entire volume. So now you can see kind of how this is looking similar to our equation of continuity that we already know. If we recall, the gradient of some sort of system that we're looking at is just seeing, what the derivative is of that gradient variable. So the derivative of the flux of A divided by each, evaluated at each position that we're looking at. And that's exactly what we have here. We have the flux of A at Z minus the flux of A at dz divided by dz. So this has the same denominator, common denominator. You can combine them, and then you'll actually flip it around because when you look at the gradient, it's going to look at your final position first minus your initial. So I'm just going to go ahead and do all these steps in one and combine this to make it a negative gradient of NA plus RA equals change in concentration, change in temperature, and then if you just rearrange, you get the exact equation that you were looking for before. So you get the negative Na, or the negative Na will add over to the other side and become positive Na, plus change in Ca, change in T, minus Ra. So this is how our equation will simplify and become the equation of continuity that we know today for one direction. So now for the next part of the video, we're going to be looking at that equimolar counterdiffusion at the vapor-liquid equilibrium. The vapor-liquid interface. So this is kind of just saying when we have equal parts vapor and equal parts liquid in a system, and we're looking at the interface, so where they meet each other and they start to kind of diffuse within each other. How is the diffusion of the liquid into the vapor counter diffused by the vapor diffusing into the liquid? So it's kind of looking how both of them are going in between each other and mixing of sorts when you're looking at that interface. So I'm just going to draw this super easy here. We just have a circle of vapor, and then on the outside we have liquid. And so we're going to be looking at this interface right here. So we have the equimolar counterdiffusion when we're looking at the vapor-liquid interface. So this is that interface right here. How is the vapor going to go into the liquid into the vapor? How does that interaction happen at that interface where it's an equimolar concentration? So that means, once again, that there's the same amount of moles of vapor as there are liquid there. So the vapor will condense here. So that means that the vapor is gonna turn into some sort of liquid so that it can mix with this liquid here. And that means that our heat of vaporization is released. And then for the liquid, it will vaporize. So it will turn into vapor. So we're kind of seeing how both sides are kind of intermingling with each other. So in order for the vapor to mix with the liquid, it has to condense, become liquid, and go into the liquid phase. And then vice versa, for the liquid, it will have to evaporate and become vapor in order to mingle with the vapor phase. And for this, the heat of vaporization is going to be used here. So that just means that vaporization, sorry. I can't write and talk at the same time. Sorry, I just wrote the wrong word. So that just means when when our vapor is being condensed and the heat of vaporization is released, it's now available for the liquid to use to become vapor and go back into the vapor phase. So it's kind of like a cycle. They kind of bounce off of each other in order for this interaction to continue happening and to keep an equimolar concentration at that interface. They both have to be constantly changing into the other one at the same time so that they can replenish what is lost and keep that equimolar concentration. So we can represent this phenomena by an equation here. So we'll recall that X is liquid, Y is vapor. So we can show that the flux of our concentration of the liquid will be multiplied by the heat of vaporization, the change in heat and vaporization, so that change in enthalpy, plus the flux of the Y, so the flux of the concentration of vapor times the change in enthalpy is going to equal 0. because these are going to be going at the same time, which means that it's going to equal 0 because there's no major concentration changes here. One is not over dominating the other. And like I said, the heat of vaporization that is released by the change from the vapor into liquid is going to be used for the liquid to change into vapor. So this delta H, for this equation I have written here, this delta H is going to be equal and opposite to each other. So these will simply cancel out, and you'll find that Nx is just going to equal negative Ny. So that flux of the liquid is going to equal the flux of the vapor. So lastly, we're going to talk about those examples and show how the total molar flux is going to relate to the molar flux of A when we have two different systems. So the first is going to be when A is in opposite direction of 2B. So that's saying that when we have A diffusing up, we're going to have 2B diffusing down. And so that means that the flux of A plus the flux of B will equal the total flux of the system, regardless what direction it is. And we can show that the flux of B is going to be equal to negative. So when B is fluxing upwards, A is going to be fluxing the opposite direction. So that'll be a negative. And you're going to need 2 flux of A to counteract the B. So since there's 2B coming up and only 1A coming down, you're going to need double the flux for A in order to counteract the 2B coming up. So hopefully that makes sense. There's just more B coming up, so you're going to need more flux of A to counteract that and make that equal. And so now we can plug in this relationship that we have into our original equation. So like I said, A to 2B, so that has A going up or down either way, and then 2B in the opposite direction. So the flux of B is going to equal the opposite direction to NA, flux of A, so it takes 2 fluxes of A to counteract the 1 flux of B due to this relationship up here. And now we're going to plug that into our equation. So the flux of A plus the flux of B, regardless signs, directions, is going to equal the total flux of the entire system, which is just represented by N. So you'll have Na plus negative 2Na is going to equal N. So then you just have that the negative flux of A is going to equal the total flux. So that means the value of the flux of A, whatever value that is, in the opposite direction of that flux is going to equal the total flux of the system. And so now if we're looking at 3A to B, so we have 3A going in one direction and 1B going in the other, we'll have, once again, our original relationship of the flux of A plus the flux of B equals the total flux. And now we have a different relationship here where NB, or the flux of B, is going to equal still the negative because the A and B are going to be going opposite directions like this. Negative 1/3 NA. So this is just showing that we have 3A coming down and only 1B coming up. So that means in order to counteract the 3A, we have to make the A flux less strong, so to the 1/3 power this time, in order for NB to be equal to that. So this is that relationship that we have here that we've developed for this question. Now we can plug that in over here once again. We get NA is going to be added to negative 1/3 NA, and that's going to equal our total N. So we have that 2/3 of NA, so 2/3 of the flux of A, that value, in the same direction is going to be equal to our total flux. So we're going to have 2/3 the value of the flux of A going in the A flow direction is our total value of our flux for the entire system. So those were all very different topics for this assignment here, but also very important things to know for heat mass transfer, and we'll be applying this stuff in the videos going forward. So it's important to kind of get just this general knowledge of mass transfer that we have here, specifically talking about changes between vapor and liquid phases, that interface, how that interaction happens, and then some sort of counter diffusion, how we can see how they counteract each other, work against each other. And so, yeah, that is going to be everything for today. Hope you enjoyed.